All right, so the answer to the first one, remember, I just wanted you to take the derivative, right? So for number 1, we should have 3 plus 10 cosine 10x. Any questions on that one? No? Okay. I think on the next one, I'm going to leave it a little more simplified or unsimplified. 4x cubed cosine of pi times x plus sine of pi times x times pi times x to the 4th. You don't need this set of parentheses here, but you do need this set because pi x is inside sine, so that pi cannot go inside.
Wait, negative sign.
Did I? I didn't put the negative here. I don't know why I didn't put negative. Thank you. That's negative sign. That okay? All right. The next one, number 3, should be secant of 3x, tangent of 3x, times 3 times x to the 4th minus 4x cubed times secant of 3x all over x to the 4th squared, which is x to the 8th. So little things that you have to be careful with here, like big mistakes I see a lot, like students right here will just put secant x tangent x. But it's 3x in there, right? So it has to be secant 3x, tangent 3x, and then that 3, students will miss that 3, right? Because you have to take derivative of what's inside. And then the rest of it's just quotient rule. So, all right, for number 4, we should have, this one's a little weird, 1 over 2 square roots of x cubed minus 4x squared plus 7 times, and then in parentheses, 3x squared minus 8x. And you can move that up on top if you want. So far, okay? All right. Number 5. So for 5, this is some chain rule here. We've got secant squared of the square root of sine of 6x plus 1. And then times, now you take derivative of the square root part. So 1 over 2 square roots of sine of 6x plus 1. And then you have to take derivative of the sine part. I'm just going to continue it down here. Times cosine of 6x times 6. Yay or nay? Yes? You sure? Okay. So number 6. So on number 6, what I would have done to start the problem is I would have rewritten it as x plus 1 over x squared minus x minus 1. I would have written it to the 1/3 power. And then use the power rule and bring the 1/3 out and subtract 1. Because, you know, on the derivative of the square root, I said it's 1 over 2 root, right? That works for square root, but that doesn't work for cube root. So you can't take the derivative of it. In other words, the derivative of the cube root of x is not going to be equal to 1 over, well, what would you do, 2? I don't know. 3? Maybe you think it's 3 cube roots of x. That's not it. Okay? It only works for the squared that way. All right? So for cube, just turn it to 1/3 and then take the derivative. All right. So with that said, I have 1/3 x plus 1 over x squared minus x minus 1, all raised to the what power? Negative 2/3. And then times, now I have to do the quotient rule. So derivative of the top is 1 times the bottom. Okay, minus the derivative of the bottom, which is 2x minus 1 times the top, x plus 1, all over the bottom squared. minus 1 squared. Yes? And I didn't ask you to clean it up. So, I mean, you could, start putting things together, but I'm just going to leave it there. Okay, number 7. This is 1 over 2 root of x squared minus 1 times 2x times x minus, I put 1 times square root of x squared minus 1, and then the entire thing over x squared. And again, I didn't clean things up, just left it like that. We are going to clean these up. I told you that already. It's just right now, this is what we're doing. So if I were to clean this one up, what I would do is I'd move this up top, I'd cancel the 2's, then I would get a common denominator between these two, and then I'd start cleaning up the fraction. So we'll have time for that later. Okay, number 8, last one. So number 8, it's pretty long, right? The derivative. So it is cosine of sine of 2x, 1, 2, 3, 4, okay, times negative sine of 2x, 4 of them there, times cosine of sine of 2x, close, and finally cosine of 2x times 2. All right, so this was just an exercise, hopefully to get you all to feel a little bit better about it. I mean, how do you all feel about this so far? Any questions? Your thumbs up? Okay. It's a little different when you're working in groups than taking a quiz, right? Because that pressure, that added pressure, you start to forget things and freak out. But if y'all are okay, then if you don't want me to do anything else, we can move on. What do y'all think? You ready to proceed? Any examples or questions on the homework you want me to do? I'm sorry?
I did right U6.
Oh, you're a little ahead? All right, so we are going to move into the next section then, since all of you seem okay. What? Okay, yeah.
Number 46.
46 in the homework? Okay, let me take a look at it here.
I think I was doing it right. The paper's just really thin, so I was running out.
46. Find the first and second derivative, right?
Yes, sir.
We can run through that one pretty quick.
Second from that.
The second derivative, okay. So we have y is equal to 4x over the square root of x plus 1. All right, so you're asked to find the first and second derivatives of this. So we want to do both. So the first derivative, we're going to use quotient rule, right? So we have derivative of this is the derivative of the top, which is 4 times the bottom, minus the derivative of the bottom. What's the derivative of the bottom? 1 over 2 square root of x plus 1. And then chain rule said we would have to take derivative of what's inside next, but it's 1. So we don't have anything else there, except for finishing off the quotient rule, which is the 4x. Then all of this over the denominator squared, but when you square the square root, it goes away. So we have that. Right? Now, we have to take the derivative again. So it might be worth our effort to put them together. Did you try cleaning up, or did you just go straight for a derivative now?
I cleaned it up to 2x over.
Okay, so you did do this, and then that, and 2. So you had something like 4 root x plus 1. Did you put that on top, or just?
I put it on top.
You put it on top? Okay, 2x on top, and then you have square root of x plus 1 here, and then on the bottom you had x plus 1. Did you do anything else algebraically before you did the second derivative?
not that x, the radical x plus 1.
You
I
moved
it up as a negative 1.
Oh, as a negative 1/2, and then from there you did the derivative, so you did a quotient rule on that?
Yeah.
Oof.
Yeah, it's not pretty.
Okay, so what Jackson did was this, and this is not wrong, it's just, you might have very ugly stuff when you do this. Jackson decided to not write it this way. He said, I'm going to write that as negative 2x, and I'm going to bring the x plus 1 under a square root on the bottom up as this. So that's just this thing written to the 1/2 and then brought up as a negative 1/2, and then all of that over x plus 1, and then you did quotient rule on that. Yes?
I
Okay.
figured that'd be easier than doing a quotient rule in a quotient.
In a quotient rule. So what I'm going to do is I'm going to finish it this way, okay, just to see if we get the same thing. And then what I'm going to do is I'm going to back up and I'm going to come back here and I'm going to clean this up first, and then I'm going to do the derivative. Okay, so working with this, let's take the derivative. So you did ultimately a quotient rule, right?
Yes.
So on that, the second derivative will be the derivative of the top. Okay, so that's going to stay, right? And then it's a derivative of this, which is 1 over 2, right? So I have 4 times 1 over 2 roots of x plus 1, okay? Minus, now I take derivative of that, right? Okay, so all I'm doing right now is taking derivative of the top. So derivative of this is this, minus derivative of this is a product rule. All right, everyone see that product? So I have to take derivative of this right here, right? And that minus sign sitting in front. So I'm going to put this in a set of brackets here. So now product rule says take derivative of this one, which is 2, times this, and then plus, right? Product rule says plus the derivative of this. So Jackson, you pulled the 1/2 out, or negative 1/2? So you've got negative 1/2, I'll put it in parentheses, negative 1/2, and then x plus 1 to the negative 3/2, because you have to subtract 1 from that. And then you also have to take derivative of what's inside, but it's 1, so we're not really even looking at that. Then times 2x to finish off the product rule. Right, so that finishes our product rule, right? This right here finishes off, so I can close my brackets. And now I'm not going to close my parentheses yet. Yes, I am closing it. So that right there is just the derivative of the top. Do you all agree? So back to the quotient rule, I'm supposed to be doing derivative of the top times the bottom minus derivative of the bottom times the top. So now I have to say times what? The x plus 1, that's the bottom. Now minus the derivative of the bottom, which is 1, so I don't need to write it, then times the top. So minus, and then now I need to write 4 root x plus 1 minus 2x x plus 1 to the negative 1/2, and then all of this over, shit, keeps going, all of that over x plus 1 squared. Yes? Okay, and that's the second derivative. It's just really ugly. So if you got that, that's correct. I mean, it's not going to look like the back of the book for sure. So let's go back and let's take a look at this expression right here. Let's take just a little bit of time to clean it up before we actually try and take the derivative again. So kind of like we did when we had limits. When you had complex fractions, fractions within fractions, the things we did in the limit was we tried to combine. We get the numerator and put them together. So let's try that. Let's see if we can't somehow get these two terms together. So we would need a common denominator, wouldn't we? So this is like over 1. And so what would I need to introduce on this fraction in order to get this to be able to combine with that? Yeah, I need to introduce square root of x plus 1 on top, square root of x plus 1 on the bottom. And I'm going to multiply that through. But that's actually a good thing, isn't it? Because when you do this times this, the root goes away, right? And you'll have your common denominator. So I know that this is going to become, let's see, I have x plus 1 on the bottom. That's this. I know these two guys are going to have the same denominator, root x plus 1. And now let's see what that the new numerator will be. This times this was x plus 1, right? And then times 4. So it's like 4x plus 1, or 4x plus 4 if you want. And then minus what? 2x. So that's coming from here, right? So that numerator minus that numerator, and that is actually not that bad. This is 4x plus 4, right? And then minus 2x. So what's 4x plus 4 minus 2x? 2x plus 4 over this denominator over x plus 1. So I think you still would say, hey, look, if I take derivative of this, you still have a quotient with a quotient. But these are the same thing almost, right? So if you rewrite this as this over 1 and then flip, right, multiply. So this becomes 1 over x plus 1. That's gone. Then can't we put these together? Because this is actually a factor. This is like, what we're saying here is we have 2x plus 4 on top. Then on the bottom we have x plus 1 to the half, that's the square root, times x plus 1 to the 1. So these two are really this, right? And then if you have the same base, different exponents, you're multiplying, you just add up the exponents. So that should be 3 halves. So we get 2x plus 4 over x plus 1 to the 3 halves. And this, I think, is a little bit better to try and take the derivative of, right? Because the derivative of the top and bottom are going to be, I think, okay. With me? So let's take derivative of this. This right here is y prime, right? Just the first derivative, cleaned up. And now to take the second derivative, we do derivative of the top, which is just 2 times the bottom. Okay, minus derivative of the bottom is a little bit messy, right? You're going to bring the 3 halves out. You're going to have x plus 1 to what power? You're subtracting 1 from 3 halves, right? So you get a half. And then what else? Times 2x plus 4. So that's finishing off quotient. Derivative of the top times the bottom minus derivative of the bottom times the top, all over bottom squared, right? So what would happen if you square this?
6 to the third.
You should get to the third power, because you're basically going to take 3 halves. Squaring it means you're going to multiply the exponents. So 3 halves, you're going to multiply by 2, right? So the 2's cancel, you just get 3. So you're going to have x plus 1 to the third power. It's prettier. It's still kind of ugly, though. I want to go a little bit further because, like I said, I've held off on this, right? Cleaning things up. I've held off, but it's not because you don't have, like you're not going to have to be able to do it. It's just that simplifying these adds a whole new element, a whole new layer of difficulty to these problems. So once we understand the mechanics of the derivative, then we can start the cleaning up. But we're kind of getting to that point now. We have to be able to do this. So let me see if I can convince you of what this is. Do you agree that this is 2 square root of x plus 1 times x plus 1 minus 3 halves square root of x plus 1, running out of room here, times 2x plus 4 all over x plus 1 cubed. So all I did there was rewrote this as this. Do you all agree with that? I mean, that's kind of where it came from, right? This is x plus 1 to the half. This is x plus 1 to the 1. And so if I put those together, I get 3 halves again. Now, why would I do that? Why would I actually do that step? Because now these both have a root x plus 1 in them, don't they? And so I can factor that root x plus 1 out. So I'm going to do that now. I'm going to factor that root x plus 1 out. So this is going to be equal to, I'm factoring a root x plus 1 out. I'm going to put a bracket here. So I took this out of this one, right? So all that's left here is what? 2 times x plus 1 in parentheses, right? 2 times x plus 1 in parentheses. Okay, minus 3 halves. And then I pulled that root out, right? So I'm left with times 2x plus 4. Right? So that's what happens when I pull that out of the top. With me? All over x plus 1. Now do you see that these two are going to reduce out also? Because this is like x plus 1 to the half. This is x plus 1 to the 1. And so you subtract cube.
Yeah.
Where's cube? Where did I pull it? Oh, cubed, yes. Sorry, then let me restate. Yeah, that's cubed the whole way. I don't know why I forgot that. I was thinking of the first derivative, wasn't I? No? Yeah. No, on the first derivative, wasn't it x plus 1? Or no? Maybe the original function. Who cares? Let's just keep going. Okay. All right, so let me just, before I do anything here, let's clean this up, because this is actually not that bad. We can distribute 2 through, right? We can distribute 3/2 through. And like everything's going to be nice up there. So we have square root of x plus 1, and then 2x plus 2 minus 3x minus 6, right? That's what we get here. 2x plus 2, and then distribute through here, it's negative 3x. Distribute here to here, we should get negative 6. And then all of that over x plus 1 cubed. Almost there. Square root of x plus 1 times negative x minus 4 over x plus 1 to the 3rd power. And there's one more thing I want to do here. Like I said, this right here is the same as x plus 1 to the half. So we have x plus 1 to the half over x plus 1 cubed. That should be x plus 1 to the half minus 3, right? That's what we do with exponents like that. Division, you subtract the exponents. So 1/2 take away 3, what is that? Negative 5/2. So this becomes x plus 1 to the negative 5/2. So my final answer is this. Negative x minus 4 over x plus 1 to the positive 5/2, because what I did is I took this answer and dropped it back down as a positive exponent. So I could have a positive exponent. And this is your second derivative. Should be, hopefully, yes? Is that the back of the book answer? So do you know now kind of what I'm saying about, like, when you look at the back of the book, you're going to see an answer, you're going to go, whoa, right? And I'm challenging you to see if you can do the algebra to get you to that final spot. Because, like I said, taking the derivative is one thing. We want to be able to do something with this. And one of the big things we're going to do with these derivatives is set them equal to 0. So would you rather set this equal to 0? Or would you rather set this equal to 0? This is much easier to work with, isn't it? But if you can't get to this, then you can't set things to 0. So the algebra is still here. It's kind of been backburnered for a while, but it's coming, all right? Okay. Any other questions? Good question.
So on the test, will we mostly be getting the raw derivative?
On this next test, I'm going to be concerned primarily with whether or not you can get the derivative just using the rules. I don't know who asked that. I just heard. Okay. So I just want to make sure you can apply the rules. The following test after that, you'll really be tested on the algebra. But I would still be practicing it because, you know, algebra is algebra. And everyone here should be able to do the algebra. But I also realize that that's the kind of Achilles heel for a lot of students in Cal 1. Is like they can do the calculus part, but they can't do the algebra part. So be practicing. All right, we're moving on. So before I start this section, I want to just talk a little bit about notation, the notation that we've been using in this class, because we're about to change our notation a little bit, or use a different one. So far, if I've been giving you something like y equals f of x, and let's just do a specific example, like x to the 4th minus 3x plus 1. Let's say I gave you that function. Y equals f of x is equal to that. then if I asked you to take the derivative, there's a couple of ways that I was doing that. I could have done, y prime, right? I could tell you find y prime, right? And everyone would understand take the derivative. I could also have written f prime of x, and everyone would have said, okay, I'm going to take the derivative, right? But there were some other notations that I showed you earlier in the class that we have just kind of stayed away from, right? So here's another notation that we could have used. I could have written dy dx. And this would tell you take the derivative of this function, all right? I could have also written this, d dx of y, or I could have written d of dx, or d over dx of f of x. So these two that I just wrote in particular, this one and this one, I want you to kind of think of it a certain way. What this is saying is we want to take the derivative of this with respect to this variable x, which means that, when we look at this, we can say to ourselves that this is a function of x. Like it is a function of x, right? You give me x, if somebody gives me x, it will spit out y, yes? And it's a function because if you graph that, it would pass the vertical line test. All right? So by writing something with this notation right there, by me putting that there, you can be assured that this graph would pass the vertical line test. So x here is what we call the independent variable. And the y over here is what we call the dependent variable. So y depends on x. You give me x, right? It's independent. You just give me whatever you want, 2, -5, 10. I plug it in, and y, the answer, will depend on that x. So when I write here, take the derivative of y, dx down here, this dx is telling you what the independent variable is. Okay? It is saying this is what we're differentiating with respect to. We're treating x like the independent variable. All right? It hasn't mattered up to this point, but now it's about to matter. So that notation is the same as this notation. Take the derivative, treating x like the independent variable of that function. So all of these notations mean exactly the same thing, okay? With me? Okay, so with that idea, let me ask you, what would d dx of x be? So if I say, hey, look at this right here. That's the function, x. And take the derivative of that with respect to x. So like treating x like it's the independent variable. What do you think that answer should be? I didn't. 1? What do y'all think? 1? So this is like our function, right? This is like our function. I'm saying the function we're taking the derivative of is x, right? So what is a derivative of x? We all know derivative of x we've set up to this point is 1, isn't it? But the reason why it's 1 is because if I rewrite this using that notation, okay, so imagine this is what I gave you right there. Replace that with x. Go back to that notation. Wouldn't you have dx over dx? And that should be 1, shouldn't it? It makes sense that that would be 1. Okay. What about, if I say take the derivative with, well, let me write it down. What would that be? That would also be 1, because it's saying take the derivative of t, treating t as if it's the independent variable. So it's almost like asking this. What's the rate that t changes if you change t? Well, that means like your rise over run, the change in one is exactly the same as the other. How much does t change with respect to itself? It should be a slope of 1 always, because it's the same variable. Understand? So this should be 1. Now, if I write what's d dt of p, that is not 1, because these two are not the same variables, right? So this is, well, we don't know actually. It's something, but we don't know what it is. What I can say is that this quantity, whatever it turns out to be, is the rate at which P changes if you change T a little bit. So if T changes, this would tell you how much P changes by. A way you might want to think about this is like, let's think of a balloon, all right? Say I start pumping air into a balloon. As I pump air in, the pressure in the balloon changes, doesn't it? So this might be asking, at what rate does the pressure change if you change the, I should use a different variable, but how about temperature? This would work with temperature. If you have a balloon in a freezer, right? And then you take it out into the hot sun, the pressure in the balloon changes. So temperature does impact pressure. So if you ask what dP dt was, this would be saying how much is the pressure changing if you change the temperature a little bit. Make sense? All right. You'll see it kind of come to light a little bit more as we do more examples, but I just want to really make sure you understand this new notation, and that anytime you have the same variable here and here, your answer is always going to be 1. All right? It's the first thing we need to talk about. Now, the next thing before we proceed is this. All right, let me try this. I'm going to put this up here. This would be a problem that would have come from last time. This is chain rule. If we're asked to take derivative here, the way we work with this was like layers, right? And the outermost layer here is that 4th power. So if we take derivative, we start with that 4th power. The 4 comes down, right? X cubed plus x plus 1. And then raise it to the 3rd. And are we done? No, very important. Now, next step is that you had to take the derivative of what's inside here. We had to take derivative of the base, which would just be 3x squared plus 1, right? That's the good old chain rule. So I'm going to put something else on the board now. Another problem. Y is equal to x. All right? Now, I'd like for you to take derivative of this. This is not a trick question. What's the derivative? It's 1. Now, you've been told it's 1, yes? I told you it's 1, and we agreed it's 1. But I want you to look at it slightly different now. Okay, do you all agree that this is x to the 1st power? So kind of like we have something to a power here. Let's try the chain rule on this and see what happens. If we did chain rule here, what would happen? 1 would come down, x to the 0 because you would subtract 1, right? And then times the derivative of what's in here, right? The derivative of that. And the derivative of that is 1. Now I'm going to write it a different way. I'm going to write it dx dx. That is still, that's what I'm saying, right? Take derivative of that, treating x like the variable. So it is dx dx, and we know that that's 1. So let's just verify that we get the same answer that we think we should get here. Anything to the 0 is 1, right? Unless it's 0 to the 0, but that's a different story. So we're saying as long as this isn't 0, anything to the 0 should be 1, right? So we have 1 times 1 times 1. So the answer is 1, which is exactly what you should have told me in the very beginning, right? Like if I say, if I walked in today and said, what's the derivative of x? Everyone would have said 1, right? Right? That's what you would have said? Okay. But do you see that you could have looked at it this way? Okay. One more time. Let's do this one more time. Okay, what if I give you this one? Take the derivative of this, but I want you to use the chain rule this time properly, like the way we did here. So the derivative of this should be 2 comes out, 2 times x to what power? 1. Now use your chain rule. Now the derivative of the base, right? And that's going to be dx dx, which is 1. Yes, I know it's 1. But that's what we're actually doing, right? And then at the end of the day, this turns out to be 2x, which is exactly what you would have said in the beginning of class. All right? I think we're ready. Implicit differentiation. All right, explicit versus, we start by just trying to understand some language here. The difference between an explicit and an implicit equation. So far, everything we've been doing in here, all the derivatives we've been studying, we've always been able to say y is equal to some function of x, and then I give you the function, then you take the derivative, right? Okay, so another way of saying that is we've always been able to isolate y. Like if we had the equation, we had two variables, y and x in there, we always had y equals something. So y was always isolated. So any explicit equation, sorry, I should not have gone that far. Okay, so to be an explicit equation means that you can express one variable, usually y, explicitly in terms of the other variable, which is usually x. So you can solve for y. All right? Some equations are very difficult to write in an explicit form. When we attempt to get them in an explicit form, we run into difficult algebra, and sometimes we obtain multiple equations. All right? Implicit, no. I think this should be, we call these implicit equations. So I'm going to give you some examples. So here are some examples of explicit equations. This first one, y is explicitly in terms of x. If you give me x, I give you y, right? This one is also explicitly in terms of y. If you give me x, I give you y. This one is explicitly in terms of y. If you give me y, I give you x, right? All of these have something in common. You can isolate one of the variables, right? Get it by itself. These are all explicit equations. Implicit ones are things like this, where it would be difficult to get y by itself or x by itself. Let's try this first one. Can you get x by, or let's do y. Can we solve that for y? I think we can try. How about we isolate it first? You agree you could do that? Now, what would it require to get y by itself? Not y squared. You take the square root. And we all know, do we know, that anytime we take the square root, you have to do what? You have to do plus or minus, right? We do that because when you square something, right, you're always going to get a positive answer, but it could have started out negative or positive, so we have to account for both scenarios. Now, if you look at this, if this is a plus or minus, then that means this is two different functions. Like this is two different things. On one hand, it's y equals the positive square root of 16 minus x squared. Or it could also be this one. So if I ask you to graph this, you're going to get a picture. And if I ask you to graph this, you're going to get a different picture, right? So there's a problem with this. This is two functions, isn't it? Two. Now, I think you could argue that we've solved for y. Right? You could argue we have, but the problem is when we solve for y, we had two different answers for it. So if we're asking ourselves, what's y prime? What's the derivative? Which one do you do? Right? Which one do you do? So that's somewhat problematic, yes? Okay, now if you're saying to yourself, but we still solved for y here, so we have something, look at the next one. How are you going to solve for y here? Let's try it. I mean, do we have any hope? Let's see. Okay, let's try and solve for y. Maybe get all the y's on one side, all the x's on the other. That might be a place to start. I don't know. Let's leave the cosine y here. Let's pull that y squared to this side. Let's get that x cubed to the other side. So that's a start, right? Right now, if somebody gave you x, you could not tell me what y is. You couldn't. Because this does not say y equals that, right? It says cosine of y minus y squared equals that. So giving somebody x right now is not enough to get y. So anything else we could do to try and get y by itself? Can't factor a y out, right? Can't pull a y out because this y is an argument inside the function. You can't pull it out. So there's just not a way, okay? There's no way to get y out. And there's not some secret algebra toolbox that we can pull out that will ever do it, okay? Just some equations we cannot explicitly solve for one of the variables, all right? It's just impossible. This one's the same way. You just can't solve for y explicitly. Now, you may be saying to yourself, big deal. Who cares? We can't solve for y, big deal. Well, what is this? Do we know what this is? If I asked you at the beginning of class or right now, do y'all know what that is like visually? Can you identify what that is? What is it? Circle, radius 4, right? This is a circle of radius 4. From college algebra, pre-cal, right? I don't know where, from somewhere, conic sections, x squared plus y squared equals r squared. So this is a circle of radius 4. So if I look at that first one, I hope we would all agree that that's not a function. It fails the vertical line test, doesn't it? Does. But we're calculus students, right? And, well, you're calculus students. I'm always a student of calculus. I'll be in there too. Okay, but wouldn't it, does that not make sense that we might want to know what the slope of the tangent line is there? We still want to be able to do the same things that we've been doing for functions. Right now, if we have a function, we can go to any point, we can find the slope of the tangent line. If somebody draws something that's not a function, we still want the ability to find slopes of tangent lines, right? So I guess what we're getting at here is this has a graph, and there are points, and there are tangent lines. We want them, right? The fact that we can't solve for y appears that it's going to be problematic, right? That it's going to be trouble for us. This one right here, do we know what that one looks like? This graph right here? A lot of you knew this was a circle. Anyone knows what this is? I have no idea what that is, okay? So let's just graph it real quick. Let's just take a look, all right? I'm going to graph it, and I'm going to go to my good old Desmos. Okay. This should be pretty interesting. I'm going to move it all the way over so you can't see it until I'm done. Okay, x cubed plus cosine y equals x plus y squared. Okay, you ready? There it is. Is that a function of x? Is that a function of x? It is not. It fails the vertical line test, yes? But does it have points that we might be interested? Does this look like something that I'm not seeing? Because everyone's got this smirk on their face. No?
It looks like a nipple.
A nipple. All right. All right. I might be interested in knowing the slope of that tangent line, right? So, yeah, that's the piercing. Right? So we still want the ability to do it. We don't want the fact that it fails the vertical line test to basically put the brakes on our calculus ability. Yes? Okay. Let's look at the last one here. Maybe it won't be so profane. Okay, so next one, cosine of x times y equals 1 minus sine y. Oh my goodness. All right. So what's that look like?
Feathers.
Feathers? You can't go from nipples to feathers now. All right, so look at this thing. This fails the vertical line test in so many respects, right? Look at this, vertical line test. Even a horizontal line test would fail on this one. But I might need to know the rate at which our graph is changing right there. Later on, this might be what we, like differential equations, we have these things called fields, and they kind of look like this, and we sometimes need to go and look at specific points on the field and figure out the rate of change there. So we want the ability to do it. And right now, everything we've done, we've needed y equals a function. That's what we've needed. Now we have a new way of doing it where we can do this. And it's called implicit differentiation. And that's what the rest of this section is about. All right? So this is me just basically saying everything I just said. Okay? So you got a circle. We want to know tangent lines. This one right here, right? We might want to know the slope of the tangent line. So look, we're gonna start with the circle. I think that's the easiest place to start, and it actually has a pretty nice geometric result. All right. So let's do this. Let's start with this x squared plus y squared equals 16. I want us to find y prime. Now, when we're dealing with implicit equations, implicit, where we know we can't solve for y. So this is not an explicit, this is implicit, right? When we're dealing with these, we do not want to use this notation anymore. We want to switch over to the Leibniz notation, which is this one. So this is not preferred. What we want to use is this instead. Now the reason why this is the preferred one is because in this notation, this indicates that we want to treat y, I'm pointing at x saying y. We want to treat the x as the independent variable, as the input. So what we're saying is, what's the rate that y will change if I vary x a little bit? Right? That's the notation here. Well, let's just do it. And you'll see in a second why that's so important. All right? I think you will. All right, so I want that, right? Find that. Okay, so what we do, what implicit differentiation is we're going to look at the equation and we're going to do something we've done a lot of times in our mathematical life. We've always done something to both sides of the equation, right? We are going to do that. We're just going to take the derivative of both sides. But we're going to do it like this. We are going to take the derivative, treating x like our variable, our independent variable on the left side. And then we are going to take the derivative, treating x like our variable on the right side. And this process right here is called implicit differentiation. All you're doing is taking the derivative on both sides. I know that doesn't seem like a big deal, but there's little technical things we have to be really careful with in here. All right? So here we go. On the left side, I'm trying to take the derivative, treating x like the independent variable of a sum, right? And the derivative rules say that I can do them individually. So this really breaks down to be the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals, now on the right side I'm taking the derivative of a constant, right? And that will never change your whole life. The derivative of a constant will always be 0, right? Doesn't matter what you're treating as a variable. If you're asking how fast, what's the rate that the constant changes with respect to something, it's always 0 because that never changes. So that rate of change is 0, always, always. All right? Okay. I'm going to pull some sticks here. I want someone to make a mistake. Maybe you won't make a mistake, and then we can call it a day. All right. So we've got Jasmine's up first. Where's Jasmine? All right, Jasmine. We need to take the derivative, treating x like the independent variable of x squared. So what do you think that is?
Do we just treat it like 2x for the derivative?
Just like 2x? What do y'all think? 2x? Okay. Yes, it is. But I want to go through and do it the way we just did it a second ago. Just this first time, I want to make sure we're all clear with it. If you're asked to take derivative of x squared, if I ask you to use the chain rule, first thing you do is bring the 2 down, right? So 2, x to what power? to the 1. Okay, now times, now take derivative of this with respect to x. So that should look like, it's 1, but I could write that as what over what?
Oh, d over dx over
Dx over dx, right? Everyone okay with that? Yes? Any questions? Sure? Okay, that's this one. Okay? Plus, now, Danielle, right? You get the next one. So now we're taking derivative, treating x like the independent variable of y squared. So do the chain rule first. 2y to the first power, then times, now you take derivative of the base. You got the trickier one. Just go with
dx over dx.
okay, you're on the right track. You want to say dx over dx because that's what happened here. But we put x on the top because that was x. Here it's what though? Y. So this is dy. That almost looks like a prime, doesn't it? I'm not going to put it there. dy dx. Danielle, does that make sense? Everybody, does that make sense? Okay, equals what? 0. Okay, now let's clean this up. We know this is 2 times x times 1. That's 1 because it's dx over dx, right? Plus 2 times y times dy dx. This is not 1. What is this? It's what we're looking for. Right? This is actually what we want. This is the rate at which y changes with respect to x. That's what we're solving for, right, Danielle? And if Danielle would have messed that up and just put 2y here without the dy dx, it would never show up, and we would never be able to solve for it. So do y'all see how important this chain rule actually is? The 2 comes out. Yeah, that's 1. Big deal. Over here, it's not 1. So my next line looks like this. 2x plus 2y dy dx equals 0. Now, what we have here is an equation, right, where we're trying to figure out what this is. And it's there, so let's solve for it. So let's move the 2x over, right? 2y times dy dx equals negative 2x. Last step, divide by 2y. Okay, so if I divide by 2y, I get what? Negative x over y. And this is our answer. Now, we need to make sense out of it. We need to make sense out of this. What was this graph again? A circle. Radius of 4. All right. Let's try something. And this is a major point, but let's see if we can understand what's going on here. This point right here, what should the slope of the tangent line be there? Should be 0, right? Okay. The formula that we came up with that gives us the slope of the tangent line, it actually requires 2 pieces of information. Do you all see that? It requires both the x and the y coordinate of the point. You know how before, when we were doing these problems, if I wanted to know the slope of the tangent line here, all I would need to know is that x value right there? You give me the x, I give you the slope. With implicit differentiation, you actually need to know, most of the problems, you'll need to know the x and the y coordinate. So what is the x coordinate here, and what is the y coordinate here? 0 and 4, right? So if I plug in 0 for x and 4 for y, I get 0, don't I? And so that matches what happens here, right? What about here? What's that point? 0, negative 4. Does that have any impact on the answer for us? No. So we get that slope, right? 0 is there. Okay, what about this point right here? What's the slope there? Can you tell me? I'm going to say that's like 45 degrees right there. Can you tell me what the slope is there? Negative 1. Why is it negative 1? If it was the unit circle, I would agree. It would be root 2 over 2. No, but you're there. You don't need to even know the points. You don't need to know what they are. You just need to know that they're the same, right? Because if you're at 45 degrees on the circle, then how much you go out and up is the same, right? So whatever the x and y coordinates are here, the x coordinate, right? The x coordinate here is positive, right? And the y coordinate here is what? Positive. And they're exactly the same, aren't they? And therefore, if I come over here and plug those two numbers in, if they're exactly the same, then that's going to be a 1, but then it's negative. So you get a slope of -1, don't you? But if you're down here, that slope of that tangent line should be +1. And it is, because here the x coordinate is positive, but the y coordinate is what? Negative, but they're exactly the same because, again, we're at like -45 degrees. So when we plug that in over here, our x will be positive, our y will be negative. Now you'll have a negative over negative, and there will be 1. So if I pick any point, now it could be completely arbitrary. If I go here to some x value and go up right here, if I want to know the slope of the tangent line there, I actually have to know that point. I have to know what the point is, the x and the y. And so can you all see that knowing the x coordinate by itself is not enough? If I go out here to this x, it could be this point or this point I'm talking about. So you have to give me both, x and y. And our formula reflects that. Okay? What about here? I've conveniently avoided this one. Yeah, what's the slope there? What's that? Undefined. It's a vertical line. Now, is that what you get when you try the formula? This point, what's the ordered pair here?
4.
This is the ordered pair 4, 0, right? So if we plug in 4 for x, there's no problem. But if we plug in 0 for y, we get division by 0, and it's undefined. And vertical lines have undefined slopes. So everything matches perfectly, doesn't it? And in theory, this will work for any relationship we have. Any implicit equation, we can always find slopes of tangent lines. We just have to be able to crank out that derivative. All right, so let's look at the next one. Should we do that real ugly one? The one that looked like a nipple, according to somebody in here, not me? Just going on the record, that was not my idea. So do y'all want to do, yeah, let's do this one. We'll go kind of little baby steps here. Let me write it down first. We have x squared plus xy minus y squared equals 4. And just so you know, that's the graph. And it does fail the vertical line test, obviously. So can we still find slopes of tangent lines here? Should be able to. Whoa. Back here. All right, so the first thing I'm going to do is I'm going to take the derivative with respect to x of the left side. And then I'm going to take the derivative with respect to x of the right side. Oh, I didn't tell you in here, find dy dx, sorry. So I'm going to go a little less detail on this. Marcus? Okay, Marcus, I'm going to have you start us out here with this derivative. So we can do these individually, right? Okay, so what is the derivative of x squared with respect to x?
2x plus dx of
It's 2x times, right? So it's, does everyone agree with that? It's 2x times dx over dx, which I'm not going to write this time. I'm going to just write 2x because we know it's dx dx.